In Chapter 3, we assumed K bar, that is capital, L bar, that is labor, and A, the level technology, were fixed. Here, we will relax some of these assumptions. Therefore, the output Y may vary, that is increase or decrease, not fixed. And chapters 8 and 9 cover one of the most important topics in macroeconomics, that is economic growth. Today, you will learn closed economy Solow model, how a country's standard of living depends on its saving and population growth rates, how to use the golden rule to find the optimal saving rate and capital stock, and alternate perspectives on population growth. We start with motivation, why growth matters. Let's start with data on infant mortality rates. So if you compare the poorest one-fifth of all countries versus the richest one-fifth, you'll see stark contrast. That is, in the poorest one-fifth of all countries, the infant mortality rates are approximately 20%, while in the richest one-fifth, it is only 0.4%. And second, in Pakistan, 85% of people live on less than $2 a day. And third reason why growth matters is that one-fourth of the poorest countries have had famines during the past 3 decades. Fourth, poverty is associated with oppression of women and minorities. So these are just a few reasons why growth matters. So what would be the possible solution for these problems that the world faces? One possible solution is economic growth, because it raises living standards and reduces poverty, and this may help reduce the problems just listed as well. Now let's look at this plot of selected countries' income per capita in 2010 in terms of US dollars versus percent of population living on $2 per day or less, which becomes a benchmark for being in extreme poverty. Here each dot represents a country. And what you can definitely see in this plot is that there seems to be a very strong negative correlation between income per capita versus percent of population living on $2 per day or less. In other words, higher the income per capita, much less people live in extreme poverty, and vice versa. And lower the income per capita, the share of the population living in extreme poverty is much higher. Now this chart illustrates the point why growth really matters. That is, anything that affects the long-run rate of economic growth, even a tiny amount, will have huge effects on living standards in the long run. And that's the magic of exponential growth. That is, as you can see, if you compare two different annual growth rate of income per capita, just 0.5% difference in this growth rate from 2% to 2.5%, you can see as centuries pass by, there's huge amount of gap between the living standards in the long run between two countries with just 0.5% gap in the average annual growth rate. For instance, after 25 years, the increase in living standard is 64% for the country with 2.0% growth rate versus 85.4% for the country with 2.5% growth rate. And after 50 years passed, 169.2% versus 243.7%. Finally, after a century passed, difference would be 624.5% versus 1081.4%. A huge difference in living standards in the long run. So if the annual growth rate of US real GDP per capita had been just 0.1% higher from 2000 to 2010, then the average person would have earned, in 2005 dollar terms, $2,782 more during the decade, and in current prices probably the figure would be a bit higher. So what are the lessons of growth theory? The growth theory tells you that economic growth can make a positive difference in the lives of hundreds of millions of people, and these lessons help us: 1. Understand why poor countries are poor. 2. Design policies that can help them grow. And 3. Learn how our own growth rate is affected by shocks in our government's policies. Now let's start building a model of economic growth. And we start this with the Solow model. The Solow model is due to Robert Solow, who won Nobel Prize for contributions to the study of economic growth. And it is a major paradigm that is widely used in policy making, and it is a benchmark against which most recent growth theories are compared. And it looks at the determinants of economic growth and the standard of living in the long run. So how is Solon model different from Chapter 3's model? 1. K is no longer fixed, and investment causes it to grow, and depreciation causes it to shrink. 2. L, labor, is no longer fixed, and population growth causes it to grow. And 3. The consumption function is simpler. 4. In Solon model, there's no government or taxes. This is done to simplify presentation, yet we can still do physical policy experiments. Finally, the fifth is the cosmetic differences, which includes things like notation and the variables that are measured on the axis of the main graph. That is, we use different case letters, that is lowercase letters, to denote per worker terms. So let's look at the production function. In aggregate terms, y equals to f of k and l. And this is very similar to the production function we worked with in Chapter 3. However, the main difference is we use lowercase letters to denote per worker terms. And this is a neat trick to help the calculation to be simpler. So here we define lowercase letter y as the capital letter Y, which is output, and divide that by L, labor, worker. So the lowercase y is output per worker, and lowercase k, which is capital per worker, that is capital letter K over capital letter L. And we assume constant return to scale, like in Chapter 3. So what it means is when you double both inputs, output is doubled, as you learned before. So for any z that's greater than 0, if you multiply both inputs by z, the output is also come out to be z times the initial output. And the neat trick is you can pick z equals 1 over L, then actually you can express this function as y over L equals to f of k over L and L over L, which is equal to 1. And you can define lowercase y being equal to f of lowercase k and 1. So because L over L equals 1, and that simplifies a lot of calculations because now instead of having two variables so that you have to take two partial derivatives, now because we express everything in terms of capital per worker, therefore there's only one variable, that is capital per worker, that explains output per worker. And the lowercase f of lowercase k means basically the production function is expressed in per worker terms, and it shows how much output one worker could produce using k units of capital. Now this is the plot of production function, that is output per worker, as a function of capital per worker. And if you plot it, you'll see that the function exhibits diminishing marginal product of capital. That is, slope is falling flatter as capital per worker increases. And the slope is change in y over change in k, which is nothing more than, by definition, marginal product of capital, which is functionally derivative of y with respect to k. And note that because we express everything in terms of per worker terms, that is output per worker is a function of capital per worker, we just need to take one derivative to find the marginal product of capital and to solve the problems here, instead of taking two derivatives to solve problems. And the national income identity is simpler than in Chapter 3 because we assume no government. Therefore, y equals c plus I. And it's also closed economy model, yeah? So there's no net export. And if you express this in terms of per workers, then output per worker should equal to consumption per worker plus investment per worker, where these lowercase letters represent per worker. For example, lowercase c equals to capital C over L, which means consumption per worker, and lowercase I is nothing more than capital I over L, which is investment per worker. Now here, lowercase s is the saving rate, which is the fraction of income that is saved, and s is an exogenous parameter. That is, people save a fraction of their income, s, which is given. Note that s is the only lowercase variable that is not equal to its uppercase version divided by L. So you assume that people save a fraction, s, of their income. That means you can assume that people consume 1 minus s of y. Therefore, the consumption function in per worker terms, c equals to 1 minus s times lowercase y. With no government, the lowercase y is the disposable income as well in per worker terms. So the Solow model assumes this consumption function in per worker terms. And now you can substitute saving per worker equals to y minus c, and substitute that consumption function into c to express y minus 1 minus s times y as saving per worker. And if you simplify, it becomes sy equals the saving per worker. Next, since national income identity is y equals c plus I, we can rearrange to get I equals to y minus c equals to sy. That is, investment equals to saving, like in chapter 3 in per worker terms. And using the result above, we can write investment per worker I equals to saving per worker sy equals to s of s times f of k. Note that although the real interest rate R doesn't appear explicitly in the Solow model's equations, but investment still depends on real interest rate, adjusting behind the scene to keep I equals sy, that is investment equals saving. Now we plot output per worker and investment per worker, which is s times f of k. So this vertical distance from horizontal axis to all the way to f of k, which is y, output per worker. Let's say at k equals k sub 1, then y equals y sub 1, which is equal to f of k sub 1. And that can be divided into two components, as you can see in this graph. That is, that should equal to c1 plus I1, where I1 is the vertical distance from the horizontal axis to s times f of k, and the difference of f of k and s times f of k would be the difference between y1 and I1, and that should equal to c1, as you see here. So as you see, saving turns into investment, that is I equals to s times f of k, and the difference between output per worker and investment per worker would be the consumption per worker. Next, let's assume Greek letter delta represents the rate of depreciation, and that is the fraction of the capital stock that wears out each period. And if you can plot this, then you see we assume delta is constant. So when you plot it, then the plot of depreciation per worker would be equal to delta k, which is going to be a straight line plot when you plot it on the horizontal axis where it represents capital per worker, and vertical axis the depreciation per worker. And here the rate of depreciation is some positive fraction of the capital stock that wears out each period. Therefore the slope is less than 1 but greater than 0 of this plot. And in this model, the basic idea is that investment increases the capital stock and depreciation reduces it, and this change in capital stock, that is Greek capital letter delta k, equals to investment minus depreciation, that is investment per worker minus delta times capital stock per worker, that is equal to changes in capital stock per worker. And since that investment per worker I equals to saving rate s times f of k, the equation now becomes changing capital stock per worker should be equal to s times f of k minus delta k. And this is known as the equation of motion for k. And this is the Solow model's central equation, and it determines behavior of capital over time, which in turn determines behavior of all of the other endogenous variables, because they all depend on capital stock per worker. For example, income per person, Y, is function of capital stock per worker, F of K that is, and consumption per worker, C, equals to 1 minus S times F of K. Now let me introduce the steady state. That is, if investment is just enough to cover depreciation, in other words, S times F of K equals to delta K, then capital per worker will remain constant as changing capital stock per worker equals to 0. And this occurs at one value of K denoted K star, called the steady state capital stock, in this case per worker. This is an equilibrium concept. And this is the plot of the steady state. That is, you draw both s times f of k and delta k, and when they cross is the point where capital stock per worker is not changing, and at steady state, so-called, at k star. Now let's see why k star is the steady state or the equilibrium point. First, let's try to approach k from below, that is in the left hand side of the k star. So let's say initially k equals k1, and at this level of k, that is at k1, investment per worker is greater than depreciation per worker. As you see, the location at k1 of the s of s times f of k, that is f of k1, s times f of k1 is at a higher point than delta times k1. And this vertical distance is the change in capital stock per worker then. That is, you invest and the investment is higher than or greater than depreciation. Therefore, there's going to be net increase in capital stock per worker by the amount of difference. And this much is where the capital stock per worker increases from K1 to the right. So it increased to K2 by the amount of difference at K1 of investment and depreciation. So because investment per worker is greater than delta K, this will increase capital stock per worker from K1 to K2. Now at K2, investment per worker is still greater than depreciation per worker, delta K. So by the amount of difference of investment per worker and depreciation per worker is what's going to happen to the change in capital stock per worker from K2 further to the right. And this will be keep going on as long as investment per worker is larger than depreciation per worker. So this increase in K continues. That is, capital stock per worker continues to grow as long as investment per worker is larger than depreciation per worker until it moves toward K star and it reaches K star. So in summary, as long as capital stock per worker is less than K star, investment will exceed depreciation and K, that is capital stock per worker, will continue to grow toward steady state level K star, that is capital stock per worker at steady state. And at steady state, at K star, that's when changing capital stock per worker is zero, as investment per worker is identical as depreciation per worker, and K, capital stock per worker, stops growing at that point. You can actually try what I just did, but at this time, starting from K that is above K star, that is to the right of it, and you'll see eventually it's gonna go to K star. So how would you do it? These are the 3 steps how you can figure this out or try this. That is, first draw the Solow model diagram, label the steady state K star when S times f of k plot crosses delta K plot. And second, on the horizontal axis, pick a value greater than K star and label it K sub 1 as the economy's initial capital stock. Then, show what happens to capital stock per worker over time. And you'll figure out whether it moves toward a steady state or away from it. So why don't you try to do that in a piece of paper, and I'll try to show it during our live Zoom session. Now let's look at a numerical example. Suppose the production function looks like this. That is, it's a Cobb-Douglas production function with exponents 1/2 for capital and labor. And to derive the per worker production function, we can divide through by L on both sides, that is y over L equals to k to the 1/2 L to the 1/2 over L. Then it can be simplified to open parentheses k over L close the parentheses to the 1/2 power. And then you can substitute the lowercase y and lowercase k for y over L and k over L to get lowercase y, now expressed as a function of lowercase k, f of k, equals to lowercase k to the 1/2 power. That means now you can substitute instead of f of k, a specific function that is k to the 1/2 power. So if you write an equation that depicts the dynamics of capital stock per worker, then the change in capital stock per worker, which is equal to s times f of k minus delta k, and you can substitute for f of k, k to the 1/2 power, therefore you can express that as change in capital stock per worker equals to s times k to the 1/2 power minus delta k, for example. And now we can assume, for instance, saving rate is given as 0.3 and rate of depreciation is given as 0.1, which means the economy saves 3/10 of income, and every year 10% of the capital stock wears out. And let's say initial value of capital stock per worker is 4.0. Hence, that means supposing the economy starts out with 4 units of capital for every worker. Then if you use Excel, you can actually get these results. That is, initially, let's say, at year 1, capital stock per worker is 4.0, and since output per worker is k to the 1/2 power, which is square root of k, you get 2.0, and consumption per worker is 1 minus s times output per worker, which is equal to 0.7 times 2, which is 1.4, and investment per worker would be s times y, which is 0.3 times 2, which is 0.6, and delta k, that is depreciation per worker, should equal to 0.1 times 4.0, which will give you 0.4. And finally, change in capital stock per worker should equal to s times y minus delta k, which is investment per worker minus depreciation per worker, which is 0.6 minus 0.4, which is 0.2. And then you can use Excel to expand it for year 2 using at year 1 value of change in capital stock per worker. So at year 2, output capital stock per worker will become 4.0 plus 0.2, which is 4.2. And then you have corresponding y, c, I, and delta k, which will lead to change in capital stock per worker for year 2 as 0.195. So you can have this feedback of it, and then eventually using Excel you can figure out that capital stock per worker approaches 9, output per worker approaches 3, consumption per worker approaches 2.1, investment per worker approaches 0.9, and depreciation per worker approaches 0.9, and at the end, when you reach the steady state, where I equals delta k, is where capital stock per worker does not change. So the change in capital stock per worker equals 0. So Excel is a useful application to actually figure this out dynamically by having these functions plotted. However, for certain questions like this, you can actually solve using algebra by substituting these numbers. So you can try to solve for the steady state by continuing to assuming saving rate equals 0.3, rate of depreciation equals 0.1, and production function is output per worker equals to capital stock per worker to the 1/2 power. And using the equation of motion, that is the equation you saw for changing capital stock per worker, equals to s times f of k minus delta k, to solve for the steady state values of capital stock per worker, output per worker, and consumption per worker. So why don't you try to do that on a piece of paper and come back for the answer. So you can solve it this way. That is, at the steady state, as a definition of steady state, capital stock per worker, the change of it equals 0. That is, change in capital stock per worker is 0. This implies s times f of k star equals delta k star, where equation of motion with change in capital stock per worker equals 0. Therefore, you can do that. And now substitute the parameters S in delta. You have 0.3, and then substituting f of k star would be times square root of k star equals to 0.1 times k star. Based on assumed values, you can derive this relation, and then what you can do is having this trick to solve. That is, divide both sides by 0.1 and divide both sides by square root of k star. And then you have 3 equals k star over square root of k star, which simplifies to square root of k star. 3 equals to k star over square root of k star equals to square root of k star. Now you can solve, that is, square both sides of the equation to get k star equals to 9. And then you can substitute for f of k star to get y star. So y star equals to square root of k star, which is equal to square root of 9, which is equal to 3. Finally, c star is equal to 1 minus s times y star. So 1 minus s is 1 minus 0.3, which is equal to 0.7, times y star we found is 3. Therefore, c star equals to 0.7 times 3 equals to 2.1. So you could see that once you figure out k star, because y star and c star are all functions of k star, you can figure out both y star and c star based on k star we found. Now we solve for steady state. We want to see what this model says about the relationship between a country's saving rate and its standard of living, that is, lowercase y income per capita in the long run at steady state. And as you see here, you're initially at K1 star, initial steady state. And then let's assume there's an increase in the saving rate. So what would happen is this. An increase in the saving rate would raise investment. This will cause the steady state K to grow toward a new steady state. The initial steady state, K1 star, will start growing by the difference between S2 f of k and delta k at K1 star. So what happened? K1 star now moves toward the right by the amount of difference, and then this will continue as long as S times f of k star is larger than delta k. But eventually it's gonna reach, because k grows toward a new steady state, it's gonna eventually reach the point where S2 times f of k is equal to delta k. So when the red investment curve is crossing delta k line, that's the point of new steady state at K2 star. So what's the model's prediction of this increase in saving rate? The model predicts that an increasing saving rate will lead to higher capital stock per worker at a new steady state. And since Y, that is output per worker, is a function of capital stock per worker, higher K star implies higher Y star. Therefore, the Solow model predicts that countries with higher rates of saving and investment will have higher levels of capital and income per worker in the long run. That's the prediction of the model. This scatter plot shows the experience of 96 countries, each represented by a single point. And here, on the vertical axis, there's countries' income per person in 2009 in log scale. On horizontal axis, you have the country's rate of investment as a percentage of output as an average between 1961 to 2009 on the horizontal axis. And each dot represents a country. And what you see is a positive trend line. So you see the high investment is in general correlated with high income per person. Now let me introduce the golden rule. Different values of S lead to different steady states. How do we know which is the best steady state? In other words, what is your value judgment? One of them is the steady state with the highest possible level of consumption, known as the golden rule level of capital accumulation. So the best steady state has the highest possible consumption per person, C star, which is equal to 1 minus S times f of k star. And there are two effects of an increase in saving rate S. One, it leads to higher k star and y star, which raises C star. However, it reduces consumption's share of income 1 minus S, which actually lowers C star. In other words, you cannot just keep increase saving rate forever. For example, when saving rate equals 1, this implies C star equals to 0. So how do we find the saving rate S and K star that maximizes C star? So the K star sub gold is the golden rule level of capital, the steady state value of capital stock per worker that maximizes consumption. So how do we find this? To find it, we need to first express C star in terms of K star. So C star equals to Y star minus I star, and you can substitute for Y star f of K star. So you have C star equals to f of K star minus I star, and because in the steady state I star equals to delta K star because the change in capital stock per worker is 0, therefore you can replace I star with delta K star. That means C star equals to f of K star minus delta K star. Then graph f of K star and delta K star and look for the point where the gap between them is biggest. So in the horizontal axis, you have steady state capital per worker K star. In vertical axis, you have steady state output and depreciation plotted. And if you plot both of them, the plot shows the corresponding steady state output f of K star and depreciation per worker delta K star for each steady state capital per worker K star. Note that this plot is different from the other Solow model diagram because on this graph, the horizontal axis measures K star, not K. And second, on this graph, the curve measures f of K star, not S times f of K. And on this graph, the only thing determined by the intersection of the two curves is the level of capital stock where C star equals 0. And we don't want to be there. And there's no dynamics in this graph as we are in a steady state because you're comparing a different steady state capital per worker which corresponds to the biggest gap between them, between f of K star and delta K star. And that gap is largest at this point. And you call this point K star sub gold, or the golden rule level of capital stock per worker. The steady state value of capital stock per worker that maximizes consumption. The vertical distance between f of K star and delta K star. So as you see, investment per worker, that is I star at golden rule is equal to delta times K star golden rule, and the difference between Y star gold and I star gold is the C star gold, and that is maximized at this point. So the C star which is equal to f of k star minus delta k star, is biggest where the slope of the production function equals the slope of the depreciation line at this point. Therefore, as you know, the slope is derivative of y with respect to k star here, of y star with respect to k star here, and by definition, that is the marginal product of capital. And then the slope of the depreciation line, which is delta, should be equal to marginal product of capital when you found the golden rule level of capital stock, which gives highest amount of consumption per worker at steady states, at different steady states. I can show you why MPK equals deltas when the golden rule level of capital stock per worker is achieved during our Zoom session. Now let's look at the transition to the golden rule steady state. That is, the economy does not have a tendency to move toward the golden rule steady state, and achieving the golden rule requires that policymakers adjust saving rate, and this adjustment leads to a new steady state with higher consumption. But you might be interested what might happen to consumption during the transition to the golden rule. There are two cases possible. Let's look at the first case. First, starting with too much capital. That is, if you draw a timeline, and initial time is t0, and you want to see what happened to y, c, and I. And if k star is greater than golden rule level initially, that is having too much capital initially, then increasing consumption c star requires a fall in saving rate. So before t0, in a steady state where k, y, and c and I are all constant, policymakers try to induce something, try to implement policies, and if they successfully do that, that is decrease saving rate at t0, the change in saving rate does not immediately change capital stock per worker, so y does not change immediately, but the fall in saving rate causes a fall in investment, because saving equals investment, and it causes rising consumption, because consumption per worker equals to 1 minus s times y. Because s is decreasing, consumption increases. And the change in consumption per worker is exactly equal to the opposite of the change in investment per worker, because y equals c plus I, and y has not changed initially. But in the transition to the golden rule, the consumption is higher at all points in time. After t0, in the previous steady state, saving and investment were just enough to cover depreciation. Then saving and investment were reduced. That is, then investment per worker is less than depreciation per worker. And this will reduce capital stock per worker toward a new steady state value. So this will lead to decrease in output per worker, decrease in consumption per worker, and investment per worker. So as you see, in the transition to the golden rule, consumption is higher at all points in time. That is, even though consumption falls, it does not fall back to its initial value, and you reach the new steady state where consumption per worker is maximized, and the corresponding investment per worker and output per worker are all lower than before. Yet the consumption per worker is still higher than before, and it's maximized at that point eventually. Next case is starting with too little capital. So before T0, in a steady state where K, Y, C, and I are all constant, if K star is less than golden rule level of capital stock per worker, then increasing consumption C star requires an increase in saving rate. So the policymakers increase saving rate at T naught, and the change in saving rate does not immediately change K capital stock per worker, so output per worker Y does not change immediately. But the increase in saving rate caused investment per worker to increase and decrease consumption per worker because consumption per worker equals to 1 minus saving rate times output per worker. And as saving rate increases, consumption per worker decreases. And the change in consumption per worker is exactly the opposite of change in investment per worker, because output per worker equals to C plus I, consumption per worker plus investment per worker, and Y has not changed initially. So the current one experiences an initial drop in consumption. In this case, if policymakers value the current generation's well-being more, they would be reluctant to adjust saving rate to achieve the golden rule, because future generations may enjoy higher consumption, but the current one experiences an initial drop in consumption. So after T0, now saving and investment exceeds depreciation. That is, investment per worker is greater than depreciation per worker, delta K, and increasing K toward a new steady state value will lead to output per worker, increasing consumption per worker, and investment per worker, and ultimately consumption ends up at a higher steady state level, as you see here. So definitely future generations enjoy higher consumption, but the current one experiences initial drop in consumption. It seems like, in practice, this would be harder to achieve, that is starting with too little capital, because it requires initial drop in consumption, and politically, if the voters are myopic, then it is hard to get passed through politically in the short run, because the current one experiences an initial drop in consumption. Also, if you care less about future generations, then the current one experiences, because initial drop in consumption, this will not be politically feasible in many cases in the short run. Whereas, the first case of starting with too much capital, because initially it increased consumption, it requires the following savings. So rising consumption would be a good incentive for both current generation and future generation to like this idea of inducing the following saving rate, which will increase consumption both now and later than before. So starting with too little capital relative to starting with too much capital is less feasible in political terms because of the reason. Current one experiencing initial drop in consumption in the second case versus not in the first case. The Solow model teaches us that we cannot explain sustained economic growth in terms of growth in capital per worker, because the economy will tend toward a steady state where capital per worker is constant. Now we want to consider population change as a possible explanation of sustained economic growth. So here we will assume the population and labor force grow at a rate n, and we assume that is given or exogenous. For example, suppose L equals to 1000 in year 1, and the population is growing at 2% per year, that is n equals 0.02. Then change in labor equals to n times L, that is the population growth rate times initial population. which is 0.02 in this case, times 1000, which is equal to 20. So that is, L increases by 20. So L equals 1020 in year 2 versus in year 1 it's 1000. So the difference this makes to the model is the change in the capital stock. That is, change in capital stock per worker equals to investment per worker minus, inside the bracket, depreciation per worker delta K plus NK, close the bracket, and which is equal to S times F of K minus delta K minus NK, or that's equal to S times F of K minus, inside the bracket, delta plus N, close the bracket, times K. Delta plus N times K is break-even investment. That is the amount of investment necessary to keep K constant. And break-even investment includes delta K to replace capital as it wears out, and NK to equip new workers with capital, because otherwise K would fall as the existing capital stock is spread more thinly over a larger population of workers. So the equation of motion for K with population growth is changing capital stock per worker equals to actual investment, that is S times F of K, minus delta plus N times K, that is the break-even investment. And the steady state capital stock is now defined by this, that is I equals to, that is S times F of K equals to, open parentheses, delta plus N, close parentheses, times K. So graphically, we just look for the intersection of S times F of K with delta plus N times K. And with this new graph, we can now figure out the effect of population growth. So what's the impact of population growth? That is, there's going to be increase in N, and the increase in N causes an increase in break-even investment. So let's say N increases from N1 to N2. As you can see, it has an effect of rotating the break-even investment line counterclockwise, as you see. So what's happening then? As it rotated that way, what happened is delta plus N times K is larger than S times F of K. So in other words, an increase in N causes an increase in break-even investment. This will lead to a lower steady state level of K, as change in capital stock per worker is negative. So the population growth would lead to, as you can see in this plot, the capital stock per worker to go down from K1 star to K2 star. So the population growth is another possible cause of an income differences across countries, as this model predicts that higher N causes lower K star. And since Y is a function of K, a lower K star will lower Y star. Therefore, the Solow model predicts that countries with higher population growth rates will have lower levels of capital and income per worker in the long run. Question is, are the data consistent with this prediction? This figure is a scatter plot of data from 96 countries, and it shows that countries with high rates of population growth tends to have low levels of income per person. As you can see, you see a downward sloping trend line. In other words, in the horizontal axis you have population growth, vertical axis income per person. What the downward sloping trend line tells is that as population growth goes higher, income per person falls, and vice versa. And this is consistent with what the Solow model predicts. So far, we've learned two things a poor country can do to raise its standard of living. The first thing was based on the first Solow model, that increase in national saving. This can be achieved by reducing its budget deficit or other means. An increase in national savings would increase output per worker, and decrease in population growth, as you just saw, would increase output per worker, therefore income per person. Now, to find the golden rule level of capital stock per worker, we can express C star in terms of K star. So C star equals to Y star minus I star. Here I substitute for Y star F of K star minus, instead of I star, substitute delta plus N times K star. And F of and C star is maximized when, in this case, MPK, that is marginal product of capital, is equal to delta plus N. Or equivalently, MPK minus delta equals to N. So here, in the golden rule, steady state, the marginal product of capital net of depreciation equals the population growth rate. I can show this also in the Zoom session mathematically. Finally, here are a couple of alternative perspectives on population growth. First, the Malthusian model, which predicts that population growth will outstrip the Earth's ability to produce food, leading to the impoverishment of humanity. So Malthus argued that population grows at a geometric rate, while food production at an arithmetic rate. So Malthusian model predicted that because of the differences in growth rates of population and food production, population growth much faster than food production, therefore you may have an outcome of impoverishment of humanity. However, since Malthus, world population has increased sixfold, yet living standards are higher than ever. So what was wrong with his model? The problem was Malthus neglected the effects of technological progress, which would more than offset population growth. In fact, today only 2% of Americans work on farms, but still manage to produce more than enough food to feed the entire nation. And Malthus could not foresee that. Next is the relatively recent Kramerian model, which was based on Michael Kramer's publication of 1993. Michael Kramer, a Nobel Prize winner in 2019 in economic sciences, which posits that population growth contributes to economic growth. And the Kramer's idea was that more people means more geniuses, scientists, and engineers, which means faster technological progress. And his evidence is from very long historical periods. That is from 1 million BC to 1990. And according to his article, as world population growth rate increased, so did the rate of growth in living standards. And historically, regions with larger populations have enjoyed faster growth. And here, more ideas, development of institutions, and property rights may have induced technological progress and industrial revolution that may eventually lead to recent economic growth.